Hi, this video is about D-latches and D-flip-flops. You already saw those building blocks in the exercises and you already know that you can store them for storing a bit. Later we will use D-flip-flops for building registers, where we, for example, can store 64 bits, or memory cells, where in each memory cell we can store 1 byte or 8 bits. Now let's review here what the D-latch and the D-flip-flop have in common and what is the difference and how could you build a D-flip-flop with 2 D-latches, what you basically already saw in the exercises. So this is just a review. Let's begin with the D-latch. You know that you find them under sequential elements here in the middle. So that's a D-latch. And you have 2 inputs. D for data, that's connected with a input device, and you have another input called clock, which I actually want to call here enable, because I want to make clear that a D-latch is called level triggered, whereas a D-flip-flop is edge triggered. And for that reason I want to distinguish the input connected with clock. Then on the output side you have Q, which basically gives you the information stored in the D-latch. Currently we store here a 0. So here we also see the 0. And the other one is Q inverse, which would be 1. But we will just use Q. And why you also have always a Q inverse might become clearer when we actually think about how to build a D-latch. Now, what you should experience is that if enable is at 0 and you change data from 1 to 0 or 0 to 1, nothing changes inside the D-latch. It's still storing a 0. But now let's change enable from 0 to 1. Then you see the information, data equal 1, was copied into the D-latch. It was moving into the D-latch, or it was flowing into the D-latch. You have some kind of information flow if enable is 1. If you now change data from 1 to 0, this information flow also happens. Yeah? So you can change it forth and back. Now, if you set enable again to 0 and change data again forth and back, nothing happens. You still keep the information stored inside the D-latch unchanged. Before I formalize that, let's look again at the D-flip-flop, which you find under sequential elements here on the left. You actually have here the same inputs on the left, D for data, that's connected. You also have a clock, which I here actually want to call clock. And you again have 2 outputs, Q and Q inverse. And again, I just use Q, because that's showing me the information stored inside of the D-flip-flop. Now actually you have a bit more. You also have here an enable, you have here a preset, and you have here a reset. This is not important for now, but we might come back to that later or in another video. Now let's play around with the D-flip-flop once more. Let's say I change data from 0 to 1. The clock is at 1. Then you see no information flows into the D-flip-flop. But if I change the clock back to 0 and then back to 1, you actually have this information flow. This information flow happens, or happened in this case, when the clock was switching from 0 to 1. And we will later call this a rising edge of the clock signal. So let's switch back the clock to 0, change data to 0. Then it becomes clearer what I mean. If I now change the clock from 0 to 1, when I generate a rising edge of the clock signal, I again have this information flow, that data gets copied into the D-flip-flop. And then I again could change data forth and back, nothing happens. Nothing happens until the clock again goes from 0 to 1. Okay, so that's what we already experienced in the exercises. Now let's describe this a bit more formal, and then we can come back to this example. In this more formal description, I want to consider these values for inputs and outputs as functions in time. That means I can draw a graph for visualizing how certain things change over time. So what you see here in short are basically graphs where the x-axis would be the time axis and the y-axis is used for the values. So of course values only can be 0 or 1, so you would have here 1 and here 0, for example. And the same thing for input D and output Q. But let's remove this axis here. I want to keep the information here as essential as possible. So let's describe that enable is in the beginning 0, then I change it to 1, I keep it at 1 for a while, then I change it back to 0, something like that. So in the beginning it's 0, that means we have a graph in the beginning like that. Here the value is 0. Then I change it to 1, that means I continue here. And actually I can draw here an edge. So here the value is now 1 for a while. And then I change it back to 0. And let's say then I change it back to 1. Of course, mathematically, this is now not a graph of a function, because in a function graph, you don't have edges like here. Or you at least would visualize this edges differently. You would, for example, use dotted lines that you actually see here some jump happens. Surprisingly, the engineers are here more precise because it's also better reflecting, as you later will see, the actual physical nature of logic gates. They would draw this like that you start with 0, then you go from 0 to 1, and they don't use an edge. They would actually just use a line like here. Then you stay at 1, then you go from 1 back to 0, then you go from 0 to 1. Because this also better reflects that in a logic circuit you have some undefined states. For example here, when the value changes from 0 to 1, then this takes a while until you actually reach the 1. There are always so-called delays involved. And during this change from 0 to 1, you have states of the logic gate which are undefined in a Boolean sense. But we will come back to that in another video where we actually deal with delays. So for now, let's simplify it as I draw it before. Now let me also show you how I, for example, now would change data over time. Let's also begin with 0. So with that, then I change from 0 to 1 instantly, or at least it seems like that. Then I stay at 1 for a while, then I go back to 0. Then I go from 0 to 1. Then I stay at 1 for a while. Then I go from 1 to 0. Then I go from 0 to 1. So this could be a description of how I was clicking before onto these input devices. Now let's also visualize here how then the state of Q changed. Now here, of course, it's interesting at what points of time data changed and enable changed. So let's use here actually dotted lines to mark this points of time. So when we look at this time frame here, enable was 0 and data was 0. That means we actually don't know the value of Q. It's just the initial value or the value of Q that we had before. So here we either could assume that initially Q was 1 or Q was 0. Let's say Q also was 0. Then we can visualize it like that. Then data in this time frame changed from 0 to 1, but because enable is in this time frame 0, this does not change the value of Q. So we stay at 0. And if Q was initially 1, we would stay at 1, of course. Now here in this next time frame, we actually have enable equal to 1. It's on level 1. That means in our understanding, Q will be equal to data. So Q also would now change to 1. Or again, if it was already 1, it would stay at 1. Then in this time frame, because enable is still at 1, we would have the same value as D. So we change from 1 back to 0. Also in this time frame, enable is still at 1. So we have the same value as D, which means we change from 0 back to 1. Then in this time frame, enable is 0. That means the change of data has no influence on Q. So that means we basically stay at 1. Also in this time frame, enable is still 0. So we stay at 1 until we reach this time frame. Then we actually go back to 0 because data is here 0. So we're here at 0. Then in the last frame, we are still in a state where enable is 1. So we copy the value of D. So we go back to 1. And if you would use actual electronic circuits, then with an oscilloscope, you actually could observe what you see here. And there you actually would see the truth that when we change here, for example, from 0 to 1, this doesn't happen instantly. It happens over time. You actually don't see here a straight line, so this might be different, but you see that somehow this change takes some time. But let's keep it simple for now. Let's assume we don't care about this delays. Then we still can characterize how a D-latch works with a simple Boolean equation. Let me show you that. I want to describe the value of Q. Well, if enable is 1, then Q is the same as D. And this expression, D and E, certainly has the value of D, whatever D is, if E equals 1. And otherwise it's 0. Now if E enable is 0, then the value of Q is the value of Q before. So I could say Q and not E. Because this expression has the value of Q if E is 0. And otherwise it's 0. Now you see, this here and this here cannot happen at the same time. In our understanding at least, you either have just 1 or 0. That means if I now use a OR, then in case of enable equal 1, I get D. And in case of E equals 0, I get Q. So with that, we have a equation, a Boolean equation, which is describing a D-latch, which is characterizing a D-latch. Now this is, by the way, an implicit equation for Q. Implicit because Q occurs here on the left-hand side and also on the right-hand side. And it's not possible to turn this into an explicit equation where Q only occurs on one side. You also will see that because of these delays, this is not a recipe for building a D-latch. It's just a characterization. But before we go into that, let's continue with looking into this D flip-flops and how the behavior is described with this positive edges of the clock signal. So here I basically just copy-pasted the graph from before. I changed the title to D flip-flop. I erased the graph for Q. And actually I should change this into clock. Now actually what you see here is not really a clock signal. In a clock signal, this here and this here, for example, would have the same width because a clock usually has a certain frequency. But let's not care about that. The important thing is that what we saw in circuit verse is that we only have to care about edges in the clock signal where we go from 0 to 1. So this edge and this edge. So this makes it easier to track how Q changes depending on D. We just have to look at this points of time. So at this point of time, we take the value of D, which is at this time 1. So the graph would change from whatever Q was initially. Let's say Q was initially 0. in this case, it would change from 0 to 1. And then it would stay at 1 until we get a new rising edge from the clock. And here at this point of time, the value of D is 0, so that would mean now we change from 1 to 0. So Q would be 0 afterwards. So I hope from this picture it's clear why D flip-flops are called edge triggers, and in this particular case positive edge triggers, because we only have to look at these 2 points in time in this example, where the clock goes from 0 to 1, where we have a rising edge. Now let's look at a more realistic clock signal, where we actually see that we have a certain frequency in the clock signal. And let's think about how to describe the behavior of this flip-flop. We only have to look at these points in time, where the clock goes from 0 to 1. And let's call the value of D in this first time frame D0, in the next D1, and so on. So we basically have here a sequence of Boolean values. And here we call the states Q0 and so on. Then we know that, for example, this value here is the same as this here. We basically have this data flow that this data gets copied into Q. And this, of course, can be described formally. We basically can say in a D flip-flop, we always have Qn plus 1 equals Dn. Now in Circuitverse, I, for example, will show you the following. I will use a D flip-flop. So we have here a D, we have here a clock, we have here Q, where I use here a NOT gate. And the output of this NOT gate goes into D. And here I have my clock signal. Now let's try to describe this with this formalism up here, so that we basically can predict what happens if we let the clock do its job. Let's say initially we store a 0 in the flip-flop. That means we have here this level, 0. That means D is, in our mathematical simplification, at the same time always 1. Then comes the rising edge. That means this 1 gets copied into Q. That means we have here a rising edge. Q1 is 1. That means D1 becomes 0. Then the things repeat themselves, just inverted. So that means we should see the following, that Q is flipping from 1 to 0, from 0 to 1, from 1 to 0. And at the same time, D always has the inverse value. So this would be the graphical description. How could we do this more formal? We say that Dn is the same as Q inverted. And here we have basically this relationship that at the same time step, D is the inverted value of Q. And that basically, if we simplify things, tells us that in the next time step, Q has the value inverted from before, from the previous time step. And this is actually, in my opinion, kind of interesting, because with a notation similar to that, you can describe in so-called hardware description languages, like for example System Verilog or VHDL, some circuit. So you use a notation like that and you basically describe a circuit like that. So in hardware description languages, you basically go in this direction. Textual description of some circuit. And we did now the opposite. We somehow looked at a certain circuit and described it formally. And I think if you're interested in this, using hardware description languages to describe hardware, it's useful if you already know this direction, if you already can look at a circuit and describe it more formally, because then it's later easier to go the way around. Okay, let's play again with circuitverse. Let's use an input for the clock signal. Let's use a D flip-flop, where I use this for the clock. And I also need a NOT gate connected to Q, and the output goes into D. And then we can validate what we predicted. Each time I change the clock from 0 to 1, the value stored in the flip-flop flips. And here, by the way, I also can show you that you, for example, can use other input devices which are nice together with flip-flops. For example, this push button. Then each time you press the button, you have a rising edge. So then you can flip it like that. Or, to give you an idea that we are actually talking about a clock, you also can use here this clock from circuitverse. And here we go. Now also make sure that it's clear that you actually have to use here a D flip-flop and not a D latch. Let's check that out. If I would use here a D latch and connect it as before, and would again use an input device for the clock signal, let's keep it at 0 first. Then first everything seems to be fine. But if I change the clock, or actually the enable, from 0 to 1, then I get an error message. Because now, of course, I have a recursion and this cannot work. But let me also give you an idea here how D latches are used for building, or how they can be used for building some D flip-flop. You can use two D latches like that, where you connect the Q from the first D latch with the D of the second D latch. And then I need again an input for the clock. Let's move it here. And I need an input for the data. So actually, let's call it data. And let's also use an output here. So this would be Q. Now I also need a inverter or NOT gate. And I do the following. So this is my clock signal. And this clock signal gets first inverted and is used for the enable of the first D latch. And the not inverted clock signal also goes to the enable of the second D latch. And then you see when the clock is at 0, the data immediately flows into the first D latch, because when it's 0, the inverter causes here enable to be true. And now if I change from 0 to 1, the data flows from the first D latch into the second. Now I can change here the data and nothing happens. If I change the clock to 0, the data flows into the first D latch, but not into the second. And now you basically see that I realized the same as I have with D latches. This here is just used as a buffer. And this here is basically showing you the actual value stored in the D flip-flop. So this is one possible way to realize a D latch based on two D latches. Some master worker pattern is used here. The engineers have a less politically correct expression for this circuit. Let me also show you how you cannot actually realize a D latch, because that is now the obvious next question. How could we realize a D latch now as we know how to use 2 D latches for a D flip-flop, let's use this characterization of a D latch. And there are actually 2 ways. I could use a multiplexer, where I say here, this here is my enable. And the output of the multiplexer could be my Q. So this would be Q. Then I also have a data, which I now connect with the input 1 of the multiplexer. So this would be data. That means, obviously, if I set data to 1 and I use enable equal 1, then the data flows through the multiplexer and Q equals data. And otherwise, if enable is to 0, Q should be the same value as before. So you basically would have this this implementation of a D latch, which is not working in real life. But here it seems to be the case. If I now change enable to 0, I can change data. The value in Q stays the same because I have here this loop. And if I change data to 0 and enable it, I'm now storing the Q. So this also could be expressed, by the way, with logic gates, with AND and OR gates. Basically the Boolean expression that I showed you before. Let's move this a bit. Let's say this here is enable E. Let's say this here is Q. This is D. Then if enable is 1 and D is 1, this should be the value. This is the first part of the equation. The first building block, then I need another AND gate. Here I want to say that if enable is false, then the output should be the same as Q. Let's start here with Q on the right hand side. So that simply would mean that Q is used here as an input. And then we had an OR, which is basically just connecting these 2 outputs. And the output of this OR equals Q. And then we have this implicit equation realized with AND gates, OR gates, and a NOT gate. And this also seems to work. I mean, if I set enable to 0, then I can change D, and the value seems to be kept. It doesn't change. If I change E to 1, then Q equals D. Then I can change it back here, enable to 0. I can change D again. So it also seems to behave like a D latch. But in real life, it's not working because all these gates have a certain delay. That means it takes a while until the output is actually what we predict in our mathematical model. And you already saw this actually in exercises, but there will be also another video where I show you in detail how to actually simulate these details. And there you will see that things will not work this way.